Good afternoon, everyone. I'm Chongqing from Southeast University, and I'm going to present our research on MCU hardware emulation. So this is a joint work with Drexel University and UMass Lowell. Nowadays, we are surrounded by embedded systems like smartwatches, smart locks, and PLCs, etc. And microcontroller units, or MCUs, are widely used in these embedded systems. There's a piece of software which we call firmware that runs on the MCU. However, MCU firmware contain vulnerabilities, just like any other software systems, which threatens the security of embedded systems. So we need to perform analysis on MCU firmware to ensure their security. We can either do static analysis or dynamic analysis, but we prefer dynamic analysis because it's more practical. However, dynamic analysis means we need execution environment for MCU firmware. Rehosting is a kind of dynamic firmware analysis technique where we try to create a virtual execution environment to dynamically execute and analyze the firmware. And naturally, we would want to emulate the hardware because once we can directly run various firmware once the hardware is properly emulated. But MCU firmware are tightly coupled with the heterogeneous hardware, and the diversity of this hardware is just beyond imagination. For example, MCU hardware consists of CPUs and peripherals. There are like dozens of CPUs architectures and thousands of peripherals. So while it might be scalable to emulate CPU architectures one by one, manually emulating peripherals is just unrealistic. Existing solutions are mostly hardware-oriented or firmware-oriented. Hardware-oriented approaches require actual hardware instead of emulating them, but hardware is not always available. On the other hand, firmware-oriented approaches can emulate hardware, but they do it in a firmware-specific way, and the fidelity and generality are limited. So we have this question: can we automatically emulate hardware with high fidelity and generality? The answer is yes. Hardware behaviors can be seen as some sort of protocols, and drivers believe so deeply that hardware functions as expected that they encode such protocols into the program to interact normally with the hardware. So if we can extract such protocols or beliefs from drivers, we can infer the corresponding hardware behaviors. And I will illustrate this point with an example. So this is a UR driver that receives data. We can see from the code that the actual data receiving action is guarded by a check against the RxNE flag. And this means that the driver believes that the data register RDR can only be read when RxNE is set, which means which we call a software belief. And this software belief is consistent with the hardware specification, where RxNE must be set by the hardware when the incoming data stored in RDR is ready to be read. However, even without reading the hardware specification, we can just infer the same hardware behavior from the software belief, because if it is not the case, the driver will never read the data. So based on this idea, we propose a tool, Perry, to automatically generate hardware models from hardware drivers. Perry takes hardware metadata and driver source code as inputs and output hardware models that can be integrated into emulators, such as QEMU. And there are 4 steps in the workflow of Perry, and I'll explain each step next. The first step is preprocessing, where we collect some useful information at the source code level. First, we are interested in code that awaits registers to be updated by hardware. So we collect loop headers to extract these loop conditions. Drivers typically use a structure to describe the physical register layout, which we call peripheral structure, and we try to locate such structures to help us identify registers. Driver functions use specific return values to indicate success of hardware operations, and we collect these return values for future use. Next, we collect driver execution traces through symbolic execution. And the big idea is to symbolically execute driver functions and observe how they interact with hardware. And to achieve this, we first need to set up the symbolic execution context, which includes like identify functions to analyze, symbolizing some values, and preparing data taint sources, and hooking some callbacks. Once we properly set up these contexts, we symbolically execute these driver functions, and we propagate taints during symbolic execution to help identify data registers. To avoid state explosion, we jump out of a loop after several iterations. And sometimes there will be conflicting constraints due to register updates caused by hardware, and we detect and remove them using checkpoints. With all these collected information, we then perform model inference, where we identify software beliefs and transform into hardware behaviors. The overall idea is to first locate specific hardware interaction actions, then construct a software belief regarding this action, and finally derive a hardware behavior that can satisfy the above belief. We summarize 4 kinds of basic software beliefs. The first belief is about reading data registers. We identify data register reads through taint tracking and extract register-related path constraints until the read action. And we have this software belief shown in the slide. We know from this belief that the hardware must satisfy the constraints when the data is ready. Otherwise, the driver will never read the data. For example, from the showing function, we know the data register is DR, and it is impossible to read DR if RxNE flag is not set in SR. So the hardware must set RxNE flag in SR so that the driver can read DR. The second software belief is about writing data registers. Similarly, we identify data register writes using taint tracking. But unlike data register reads, we only care about successful data transmissions. So we extract constraints from execution path with a success return value and have this software belief. So this belief means that the hardware must satisfy the constraints after data transmission. Otherwise, the data transmission would just fail in the driver. So we have this behavior, hardware behavior. For example, we know the data register is DR, and the transmission fails if the TXE and the TC flags of SR are not set. So we know the hardware must set these 2 flags so that the data transmission can finish. The third software belief is about updating non-data registers. So updating a register may cause the update of another register. This behavior is reflected in the code as waiting registers to be updated after reads or writes. And we identify such code patterns and construct this software belief. This belief actually means that the hardware must update R2 to satisfy the waiting condition after R1 is updated in a specific way. Otherwise, there will be an infinite loop in the driver code. So we have this hardware behavior. So for example, we can see from the code that the driver waits flag 2 of R2 to be set by the hardware after flag 1 of R1 is set by the firmware, which means the hardware must update flag 2 of R2 after flag 1 of R1 is set. Otherwise, the driver will get stuck. The final software belief is about handling interrupts. A peripheral may have multiple interrupted events, but only one interrupted line connected to the interrupt controller. So interrupt handlers or interrupt service routines first demultiplex interrupt events based on register values, then handle these events accordingly. So if we can locate interrupt handling actions, we can know from the path constraints when interrupts are fired by the hardware. We observe 2 kinds of interrupt handling actions, reading or writing data registers and invoking callbacks. So we collect path constraints until these interrupt handling actions and calculate a disjunction of these constraints at the interrupt firing condition. So for example, there are 2 interrupt events, TXE and RxNE, and the hardware fires interrupts when TXE IE is set in CR and TXE is set in SR, or when RxNE IE is set in CR and RxNE is set in SR, according to the path constraints. And with all that information available, the final step of Perry is to synthesize a working hardware model using the inferred hardware behaviors, and we adopt a template-based method. So we create a template hardware model and leave some of the required information as holes, and later we fill in these holes with the inferred hardware behaviors. So for example, after receiving or sending data, we need to update some related registers. And after updating registers, we need to update related registers and check if we need to fire interrupts. And all these specific contents are generated based on the inferred hardware behaviors. We implemented a prototype of Perry and evaluated its performance. Parry uses symbolic execution, so we first evaluate its efficiency. We generate MCU hardware models using 10 driver libraries from 3 top MCU vendors, and over 30 MCUs are covered. The consumed time is shown in the figure, and Parry takes from 0.3 seconds to 9 hours to synthesize one model. We then evaluate whether the inferred hardware behaviors are consistent with the actual hardware. So P2IM provides 66 valid unit tests to test hardware functionalities, and we run these unit tests using the generated models, and as a result, we pass 49 out of these 66 unit tests without any manual intervention. And SMU is a prior work that tries to generate hardware models from hardware specifications, but it passes none of these tests without manual intervention. If the generated hardware models are actually consistent with the hardware, they should be universal enough to emulate various firmware. So we emulate 29 firmware samples and check whether the emulated firmware can execute expected functionalities. And in the end, we successfully emulate 20 firmware samples without manual intervention. And here's a small video about how we interact with an emulated shell program. And finally, the generated models is not 100% accurate, which means we need to fix them. We introduce like 35 lines of code to fix all these generated models to successfully emulate all the used firmware samples. And it takes at most 4 lines of code to fix one model. But once the model is fixed, we can use it to emulate various firmware. We also use Parry to perform 3 security-focused tasks. The first task is to find specification-violation bugs in drivers. So as has been said, hardware behaviors are actually some sort of protocols, but drivers may break such protocols when they interact with hardware. And we cross-checking hardware behaviors inferred by Parry with those defining the specification to find such violations, and we successfully found 2 violations. We also use the generated hardware models to reproduce 2 vulnerabilities in Zephyr's BLE host protocol stack. We emulate the vulnerable BLE host with the generated model, and we connect the emulated BLE host with a real BLE controller via a HCI proxy. And the emulated host can communicate normally with the controller, and then we inject malicious payload after the BLE connection is established to trigger these vulnerabilities. And finally, we try to emulate and fuzz RTOS with the emulated hardware. We implement like 11 fuzz drivers and various synthesizers for RTOS, and we finally find 7 zero-day vulnerabilities. An interesting phenomenon we observed is that we know synthesizers introduce instrumentations and shared memories, but unfortunately, the onboard flash and RAM regions are too small to hold them. But we are doing emulations, so we just increase the sizes of the emulated flash and RAM regions to make these synthesizers work, which would not be possible if you are using a physical device. So to conclude, drivers can help model hardware behaviors, and we've developed such a tool, Parry, to generate faithful MCU hardware models, which can be used in various security-focused tasks. Parry is available on GitHub. You can scan the QR code to access it if you are interested. So that's the end of my presentation, and I'm happy to take questions.